Hello, everybody. It's an honor to speak here at FOSDEM, even if remotely this time. My name is Andre Stoltz, and I work on a decentralized social app called Manyverse, and I also work on SSB, the protocol that powers Manyverse underneath. Everything that I will speak here today obviously is free and open source. Sometimes our code is licensed to AGPL, sometimes it's LGPL, sometimes it's MPL, sometimes it's MIT. A brief introduction of SSB in case you've never heard of it. It is a decentralized protocol, or in other words, a peer-to-peer protocol with the primary purpose of enabling social networking use cases. It was created in 2014 by Dominic Tarr, implemented first in Node.js, which is the main implementation, but we also have implementations in Go, C, and Rust, and these are used also in production, so they're not just proof of concepts. A basic summary of SSB is that it's a local first database, cryptographically signed and replicated peer-to-peer. That means that all of the posts that you create, or the likes, or any kind of content, they are stored first in your database on your device on a thing called an append-only log, which is essentially an array that keeps on growing, and it's stored obviously in disk. Each of these messages that you create, they are cryptographically signed by a cryptographic key pair that you own to sort of prove that this is mine, so that when you spread them, they're not forgeable or modifiable by other people. And your messages can be sent to other people by peer-to-peer. So that means that whenever you connect to Bob, it could be directly, let's say even in the same Wi-Fi or LAN. Then you send updates to Bob that, hey, here are the new things that I created. Bob also sends back to you. And we support all kinds of connections. We can do this through intermediary servers over the internet, or directly, or through a DHT. There's all kinds of ways. And this last part of the peer-to-peer replication is obviously what makes it very social. Now, SSB has been working very well, actually. It's sort of a 5-year-old social network with a lot of content, and it has a lot of people, like, over 20,000, something like that. And it's been working well, but the biggest problem that people experience in SSB, that almost everybody experiences once they join it, is called the initial sync. Now, that's a big problem, and it can be summarized like this. So let's say that Alice is an old user already in the network, and her log is usually around the order of hundreds of megabytes large. 500 megabytes or more is very realistic. And then she invites Bob to join, and Bob, once he connects with Alice through some way, then he will start replicating everything that Alice has posted. So obviously this is heavy for bandwidth, but at the same time, what's happening is that Bob's database is being indexed for queries to run better. And this is a process that is very heavy, both on bandwidth and CPU. And what happens is that this takes around from minutes to hours. It could take like 3 hours, realistically. And it's pretty bad. So people don't find it, they find it difficult to stomach, and sometimes they just quit in between. It also has an sort of side effect that people end up being more committed to the network because they've passed through this very heavy process. But ideally, we would like to optimize this and fix it. So there's a bunch of ideas here that are not the best. For instance, all of these indexes, they do their own scan of the log. So they decide, okay, I will create my index, I will scan the entire log. So the next index will also scan the entire log. They don't share that scanning. And the log, all of the messages are written in JSON. So when the indexes are being created, let's say I want to have an index only for the authors. So let's say, give me all the posts by this person. Then you have to pick the author field inside the JSON, and that means you have to do a JSON parse for that message just to pick the author field. So that's kind of, heavy. So what we did is that last year we applied for a grant in the European Commission called NGI Pointer. NGI stands for Next Generation Internet, and it's a really nice thing. And we received the grant. So we are a core team of 4 people, and that's me, Anders, Zena, and Henry, and these are our GitHub handles. So one of our goals in NGI Pointer is to improve the performance of initial sync. It's, I think, one of the 3 goals that we have. So we decided to do that by rewriting the database. So the legacy database is not only slow, it also has some other legacy decisions that set us back, such as quirks in the API and so forth. So the new SSB database has a couple of ideas. It has 3 main ideas and a little bit of additions. So I'm going to go through each of these. And the main idea is that it's encoded in BIF, not JSON. I'm going to talk about BIF. It uses BitVector Indexes, Prefix Indexes. Indexes are created just in time as opposed to everything up front. And it also supports LevelDB indexes. The old SSB database also supported LevelDB indexes since always, but we wanted to keep that because we need it in some cases. So let's talk a little bit about this format. The old log used JSON, which I don't think I need to explain. And the new log uses a new format called BIF, binary in place format, which Dominic Tarr created actually. And we started using it. It hasn't been used in production yet. And it's in binary, so we store binary, encoded, I guess, as UTF-8 for strings. So take an example here. Let's say a piece of JSON that, let's assume that this is stored in the old SSB database. How would that look like in BIF? So it's basically encoded as binary. So we have a bunch of hex representations of the binary. And if you notice ASCII, then these fields are basically the same fields that we had before. And we have these other fields that are marked in red, which I'm not going to get in too much details right now, but they are the so-called labels or tags that can tell us, what this is. Is it an object? Is it a number? Is it a string? That kind of thing. So for instance, if you focus your attention on 22, the label 22, it sort of describes what comes next here. It's trying to describe the number 20. So how does that label look like? Let's focus our attention on that label 22, and in binary it's 00100010. And what that means is that in BIF, we pick the 3 last bits as the type. So it could be either string, object, number, array. We're trying to encode all of the typical things that you would see in JSON. And the other 5 bits are used for the length. So 00100, that means 4 in binary, and that means 4 bytes. And the type means 2, and that's just a number that we chose to describe the type. So we have other numbers here. If the number would be 0, that's a string. This is just a convention that we found. And 7 is used for reserved, so we don't use that yet. And booleans are sort of combined together with null. There's a special rule for that. But this is like enough to cover all of the JSON things, right? This is everything that we need for now. So that's kind of how this works. This tag, for instance, will describe that, it's type 5 and the length is 27. These are actually stored as var ints, so sometimes they are 2 bytes, sometimes they are 1 byte. As you can see, this one is 1 byte, but because the length is so big, we actually needed more. So this says that the following 27 bytes describe this object. So if I count this 1, 2, 3, 4, 5, 6, 7, if I get there, it's 27. Just trust me, or you can do it yourself. But what this allows is that if I'm not interested let's say that I'm looking for object dot other. Okay, so I start scanning here, and I know I can skip this one because this is a string, or maybe not exactly this one. I would. Well, the point is that these lengths are very useful because they allow us to skip parts in this whole encoded thing. So let's say if I'm looking for something specific, I can, instead of parsing the whole thing like JSON parse does, I can skip based on these byte offsets if a field doesn't interest me. So that property is very important for us because then it allows us to start building the indexes. And if we say I'm only interested in author, and if you bump into a bunch of other fields that are, let's say, arrays or numbers, then you know I don't want these. You can just skip them based on the byte offset. This is what this slide is all about. So that's the important part here. So BIF is quite nice for performance when it comes to decoding. So let's say that we're reading the whole log and we're trying to find the author field. BIF is faster than doing JSON parse by 6 times, and that's really good. Now, the funny thing is that BIF is actually 5 times slower than JSON when it comes to writing. So we take the object and then we start writing it in binary in BIF. That takes more time than doing JSON stringify. But that's okay because Scuttlebutt has the use case of like, well, you're not going to be creating a bunch of messages in one go. Like, that's not the use case because you create a message by interacting with the social network, right? You do a like and you do another like. You don't do like, now I will create 10,000 likes as fast as I can. That's not a social network use case. So that's not a problem for us that it's slower than JSON. What we really need is that when we're building the indexes, it's very quick to pick a field when we're scanning the log. So that's a really nice property, and it helps us. The other idea in the new SSB database is BitVector Indexes. BitVector Indexes are something actually quite common in other databases. In any sort of real database used in production, they use BitVectors. But it hasn't been a thing in Scuttlebutt, so we thought about adding that. And it works essentially like this. Let's say you have the log of all of the messages, and you just want to ask a question like, is this message a post or is it a like? And it's a binary question. You can answer it in binary. So we can just assign 0 or 1 depending on the type. And remember, when using BIF, we can just skip all the fields inside the message, and we can choose the type field and check is it post. And answering this in binary is really nice because, as you see, 8 of these messages will cover just 1 byte, and 1 byte is very little amount of storage. So actually, to store like millions of messages or hundreds of thousands of messages, this index, if we save it as a file, it actually occupies just like 200 kilobytes or sometimes less. And that's really nice because it means that saving these is very fast, but also we could load the whole thing in memory if we wanted to, and it's not a big cost for memory. So that's nice. And this is called a BitVector index. It can be saved as a file, for instance. The other nice thing about BitVector indexes is that you can do bit operations on them, bitwise operations such as AND. So you can ask a question such as, what are all of the messages that are type post, and what are all of the messages that were authored by me? Both of these questions can be answered in a binary way, so you can get BitVector indexes out of them and just apply a bit operation of AND. And what you get as a result is all of the messages that are type post that I created. And that's nice. Now let's say, okay, this is the result BitVector. How do I get these messages from the log? So the first bit refers to the first message in the log, the second refers to the second message in the log, and so forth. And we have a special index called sequence to offset. that will say that the first one is stored at byte 0 in the log. The second one is stored at byte 93 in the log, and so forth. So that we can just apply those positions that have 1 and pick the numbers such as 93, 134, and 450. And then we know the positions in the log that we can use to read the message. So this is actually quite fast. It works nicely because these positions are all byte offsets, and that's fast to do, to read them. So that's nice, and BitVector indexes are actually really nice when it comes to performance. You can do queries very quickly, you can build them very quickly as well. And we added another idea called prefix indexes. So they're quite similar to BitVector indexes. Let's say you have a binary question such as, does this message refer to another message? For instance, if you create a like, right? A like is essentially a message that points to another message and says, I liked it, right? So let's say you have many threads, right? Then you can ask, does this thread, let's say that the thread ID is M3C2DRJK something. And then you want to know, what are all the messages that have this ID? That's a binary question, but it's a bad idea to do that, because if you have thousands of threads with different IDs, then you're going to create thousands of indexes, and that starts to be bad, because maintaining all those indexes, loading them in memory, is just not a good idea. But what we can do instead is that instead of asking this, we can ask, in this message, what is the prefix of the message ID that it's referring to? So basically, like let's say that this is a post, it doesn't refer to anything, then well, it doesn't refer to anything, it's 0. But let's say that this one was vote, and it's voting on another message, which has the ID F1B9734692. Then we can just pick the 4 bytes or something like that of that ID, and we can say that this is the prefix, and we are answering the question. And then we keep on doing that. If a message is a vote and it refers to another one, then we pick the prefix of that message's ID and we store it. And then we have this, and this is a so-called prefix index. And it's useful because we can ask better questions on top of the prefix index, such as, does the message make a reference to the message ID M3C2? The same message that the same question that I originally had here, right? It's the same question, but now using the prefix index, I can answer this. For instance, well, this the first message, let's say that it's a post, it's not referring to anything else, so no, it doesn't make a reference to that message. So I'm looking for M3C2. Well, obviously that doesn't match F1B9, right? The first prefix part is not matching, so that's also no, and so forth. But here the prefix matches, and the answer isn't a yes, the answer is a maybe, because there may be another message that has the same prefix, but the full ID is different. So that gives us a maybe. So what do we do with the maybe? We basically go to the log, fetch the full record, and then we check, is the full ID exactly what I'm looking for? Then we can finally answer yes or no. So it might seem wasteful that we have all these maybes and we have to look in the log to see the real answer. But in reality, these prefix indexes are chosen to be small enough that they are small to save, but large enough so that they're unique in this space. So this kind of works like git commit SHA IDs. So usually the full git commit ID is like a huge thing. I don't know what, 32 characters, I don't know exactly. But usually 8 is enough to identify identically, uniquely. And that's our case as well. I mean, we could obviously also store the full ID here, but it's it's going to be a much bigger file to store this prefix index. And it's actually a good trade-off, because usually there's just one or two messages that have exactly the same prefix. So that's nice, and it works. Prefix indexes are really useful for asking things like, what are all the people who mentioned me? Can I please see all the messages that mention me? Things like that. So the next idea that we have in SSB DB2 is what we're calling it, is just-in-time index creation. And that means that when we make the query, and this is our API, by the way, our query would be something like, I want posts that mention Alice. So we use an AND here. This will be automatically matched to an index. So we need a BitVector index that answers this binary question. And if that index doesn't exist by the time that we create this this query, we will create the index. So it's just in time. So we don't need to beforehand specify. These are all the possible queries that I would like to run. We can do that at the time of query. And it's pretty fast, because the index creation at the first time takes around 3 seconds in the worst case, but that's just the first time you make the query. After that, it's going to be in the order of a few milliseconds, like 20 milliseconds. So we can use in this API either BitVector indexes or prefix indexes or level DB indexes, and we can all use them in the same one. Yeah, so that's essentially most of the ideas that we use, and it's actually very nice in terms of performance. With our micro benchmarks, we figured that it's roughly 9 times faster than the previous database. And we're slowly starting to use it in production. It's currently in Manyverse used just for the votes. So all this voting system uses votes, and likes are the same concept. In Manyverse right now, it uses the prefix indexes from DB2. But it's still roughly untested in production, because we still have to convert the full, all of the use cases of database to DB2. And that's a lot of work, but we're going to get there. We're quite excited about this. I think both in terms of API, as you saw, this is a very nice API compared to previous SSB database that had all kinds of different modules that you have to load. And it's faster. I think the speed is the biggest thing that we really needed, because as you heard, initial sync is a big deal and we want to make it faster. Our goal is to make it 10 times faster if we can, and hopefully we're getting there. I'm open to questions. If you have questions, I'm just gonna basically predict one of the questions that people could ask, and that's, well, why are you creating your own database? That sounds like a very difficult task, and there's a lot of databases out there that are off the shelf and they are good. That is true. And there's SQLite has been mentioned a lot of times for us, but it's a very different use case. So SQLite is table-centric, right? It's a relational database. And it's structured, so it means that there's a schema, and it's also mutable. So mutating the table entries is common. But SSB works in a very different way. We have the append-only log, and it is unstructured. So it means it doesn't really have a schema. And that's because Bob or Carla could be posting messages of whatever type that they want, and because there's no authority in the system, there's no way of saying that's a wrong message. We can't actually force anyone to write messages that fit the format that we want. So it is unstructured by nature, and we have to deal with messages being potentially very, very out of our expectations. And then it's immutable. So once you write something, there's no way of deleting it. I mean, obviously you could delete it locally, but you can't delete it globally. And there's a bunch of problems regarding that space if you delete stuff. So we've just decided for now, let's not mutate anything. So it's a very different world, and unfortunately there's not a lot of off-the-shelf databases for peer-to-peer protocols. It's not really a use case that enterprise is usually interested in, so it's not something we easily find out there. That said, we are using LevelDB, which is very well proven. And LevelDB is essentially a so-called B-tree index, and it's it uses the B-tree. And LevelDB is well proven, and we use it. Most of the databases also have BitVector indexes, so we're basically copying good ideas from established databases. So yeah, most of the databases have some kind of B-tree and some kind of bit vectors for their indexes. So we're trying to cover those areas here with this new database. I'm really excited about it, and I'm open to questions. Hopefully also we have Anders in the chat, and we can answer the questions that you have. Thank you for listening. And that's my talk.